In episode 51, titled Data Quality Problems, Missingness, Noise, Duplicates, and Inconsistency, the main idea is that you should fix data quality issues before you blame model performance, because many model problems are actually data problems wearing a different mask. A model can only learn patterns that exist in the data it receives, and if the data is incomplete, mislabeled, duplicated, or inconsistently formatted, the model's output will reflect those defects with impressive consistency. The exam cares because data quality is a core competence in analytics, and scenario questions often hide the true issue inside a subtle quality defect that makes every downstream analysis unreliable. In real work, data quality is also a trust issue. If the foundation is unstable, every result becomes harder to defend, even if the math is correct. When you develop the habit of diagnosing quality early, you shorten troubleshooting cycles and make conclusions more credible. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Missingness is one of the most common quality problems, and the first step is to identify patterns so you do not treat all missing values as the same kind of absence. Some missingness is effectively random, meaning values are missing without an obvious link to the value itself or to other variables, and that typically reduces efficiency more than it creates bias. Other missingness is systematic, meaning a specific process, system, or workflow stage fails to capture data, and that can bias results because the missingness is tied to operational context. Segment-specific gaps are especially important because a field might be well populated for one region, platform, or customer tier and largely absent for another, which means naive summaries and models will behave differently across segments. The exam often expects you to notice this by reading scenario clues about data sources or coverage, and then to reason that missingness can distort comparisons if it is patterned. A careful approach describes missingness not as a percentage alone, but as a map of where missingness concentrates and what that implies for representativeness. Noise is another concept that needs context, because not all variation is error, and not all error looks like variation. Random measurement noise can come from sensors, logging jitter, human entry variability, or rounding, and it can obscure small effects while leaving large patterns intact. Meaningful variation is the real signal of different behaviors, different conditions, or different states of the process, and distinguishing it from noise requires understanding how the data is generated. If a latency metric fluctuates by a few milliseconds due to instrumentation, that may be noise, while hour-to-hour swings driven by load might be meaningful variation tied to demand. The exam often frames this as deciding whether variability should be smoothed, aggregated, or modeled explicitly, and the correct reasoning depends on whether the variation reflects a real phenomenon or a measurement artifact. A strong narration explains what the measurement process would naturally produce and uses that to judge whether variability is plausible signal or likely noise. Duplicates can quietly poison both descriptive analysis and modeling by inflating counts, overstating certainty, and creating patterns that are actually artifacts of repeated records. Detecting duplicates begins with keys, meaning you define what makes a record unique for the unit of analysis, such as 1 row per user per day or 1 row per transaction, and then you check whether the dataset violates that rule. Near duplicates are trickier because they may differ slightly due to time rounding, formatting differences, or minor value changes, yet still represent the same underlying event captured multiple times. Suspicious repeated records can also indicate integration issues, retries, or looping pipelines, and those patterns often show up as bursts of identical or nearly identical rows. The exam may present a situation where counts look too high or where an outcome rate seems implausible, and the correct response can be to suspect duplication rather than to invent a complex behavioral explanation. When you handle duplicates carefully, you are protecting the integrity of your denominators and the validity of any inference you draw. Inconsistent formats are a more visible problem, but they can still be underestimated because small format inconsistencies can create large analytic errors. Dates can appear in multiple conventions, time zones can differ by source, separators can change, and even the presence of leading zeros can change how identifiers match across datasets. Units are especially dangerous because mixing milliseconds and seconds or dollars and cents will generate outliers and false trends that look like dramatic phenomena if you do not normalize early. Text inconsistencies like casing differences, trailing spaces, and inconsistent separators in compound fields can fragment categories and inflate cardinality, making a clean concept appear as many distinct values. The exam often tests this by describing data from multiple systems and asking what to do first, and normalization of format and unit is frequently the safest early step. When you narrate format inconsistency, you should emphasize that consistency is a prerequisite for meaningful aggregation and comparison. Standardizing categories is another foundational step because categorical fields often encode the same concept under multiple labels, synonyms, abbreviations, or legacy naming schemes. Resolving synonyms requires a consistent mapping so that United States, USA, and US are treated as the same category if the analytic intent is the same location. Merging rare labels must be done carefully because rare categories can be meaningful, but they can also create sparsity that destabilizes models and makes estimates unreliable. The exam expects you to balance these considerations by merging only when it preserves meaning and improves reliability, rather than collapsing categories in a way that loses important distinctions. Category standardization also includes resolving typos and inconsistent punctuation, which can create duplicate categories that look different but mean the same thing. When you do this well, you reduce noise in categorical representation and make both summaries and models more stable. Label noise is a special and often underestimated data quality problem because it corrupts the target variable rather than the predictors, and that can poison learning in ways that are hard to diagnose later. Label noise can come from human judgment errors, delayed updates, inconsistent definitions, or automated rules that sometimes misclassify events. When the target is wrong, a model can learn to fit the noise, reducing generalization and creating patterns that appear inconsistent because the training signal is inconsistent. The exam may describe a scenario where a classifier performs strangely or where performance does not improve despite better features, and the root cause can be unreliable labels rather than insufficient modeling. Label noise is also a causal hazard because it can distort estimated effects by mixing true outcomes with misclassified ones, making interventions appear weaker or stronger than they are. A careful approach treats label quality as a first-class concern and recognizes that improving labels can yield more benefit than tuning model parameters. Validation rules are a powerful way to detect impossible combinations of values because many quality defects are not visible when you inspect one field at a time. A record might have a closed status with a missing closed timestamp, or a negative duration with a valid start time and end time, or a country code that does not match a postal code format. Impossible combinations also appear when fields are logically dependent, such as a feature indicating a high severity incident, while the impact field indicates 0 affected users, which may signal inconsistent ingestion or incomplete updates. The exam often expects you to reason about these logical constraints because they reflect real system invariants, and violating them is a strong quality signal. Validation rules are not only about catching errors, they also clarify the definition of valid data so that cleaning decisions are consistent and defensible. When you narrate validation, you emphasize that cross-field logic catches defects that single-field checks miss. Choosing between imputation and deletion depends on missingness type and impact, and the exam typically wants you to demonstrate that this choice is not a one-size-fits-all decision. If missingness is effectively random and the missing rate is low, deletion may be acceptable because it simplifies analysis without heavily biasing results. If missingness is systematic or segment-specific, deletion can distort representativeness by removing a particular population. So imputation or a missingness indicator may be more defensible depending on the context. Imputation itself must respect the data generating process, because naive imputation can create artificial certainty and blur real differences, especially when missingness is informative. The exam often rewards answers that explicitly tie the choice to the mechanism of missingness and to the stakes of bias versus variance, rather than to convenience. A disciplined narration states what you believe about missingness, how that belief affects bias risk, and what choice best preserves validity for the intended use. Cleaning has its own pitfalls, and one of the most serious is leaking target information into features through the way you clean or transform data. Leakage can occur if you use information that would not be available at prediction time, such as imputing a value based on future data or using post-outcome fields to correct pre-outcome features. It can also occur if you compute a global statistic using the full dataset, including the evaluation period, and then apply it to both training and evaluation, effectively letting the model benefit from future information. The exam often frames this as avoiding contamination between training and evaluation, or avoiding post-event data in predictors, and cleaning steps are part of that discipline. A safe mindset is to treat cleaning as part of the modeling pipeline that must respect time ordering and decision context, not as an offline activity that can use everything. When you narrate this clearly, you show that you understand that validity can be broken by well-intended pre-processing. Documentation of cleaning decisions is essential for reproducibility and auditability, and the exam may treat it as a governance competency rather than a technical detail. Reproducibility means someone else can apply the same steps and obtain the same dataset from the same raw inputs, which is required for scientific credibility and operational stability. Auditability means you can explain what you did, why you did it, and how it affected the dataset, which matters for compliance, incident reviews, and stakeholder trust. Documentation should include what rules were applied, what thresholds were used, how missingness was handled, how categories were standardized, and what records were excluded, because those decisions shape results. In many organizations, cleaning decisions become policy, and policies need clear rationale and traceability, especially when they affect automated decisions. When you develop the habit of documenting cleaning, you protect not only your analysis, but also the organization's ability to defend decisions later. Communication is the final step, because even the best cleaning work fails if stakeholders misunderstand the quality limits and overtrust conclusions. Quality limits include coverage gaps, label uncertainty, measurement noise, and residual inconsistencies that you could not fully resolve, and these limits determine what you can claim with confidence. Communicating limits does not weaken your work, it strengthens it by aligning expectations with reality and preventing misapplication of results. The exam expects you to express uncertainty appropriately, because overclaiming in the presence of known quality defects is a sign of poor judgment. A good communication stance describes what was fixed, what remains uncertain, and how that uncertainty might affect decisions, such as whether results are stable across segments or whether certain outcomes are undercounted. When you communicate quality clearly, you give decision-makers the context they need to use the analysis responsibly. A useful anchor memory for this episode is: quality drives trust, trust drives decisions. If the data quality is poor, trust should be limited, and decisions should be cautious, scoped, or delayed until quality improves. If the quality is strong and well documented, trust can be higher, and decisions can be more decisive because the evidence foundation is reliable. The anchor also helps under exam conditions because it reminds you that quality is not an isolated technical task. It is directly tied to whether conclusions are actionable. It also explains why many correct answers prioritize early quality checks over sophisticated modeling, because advanced methods cannot rescue corrupted inputs or unreliable targets. When you apply the anchor, you naturally choose steps that strengthen the foundation before you optimize the structure built on top of it. To conclude episode 51, you were asked to list 3 quality checks you run first every time, and the best way to handle that in narration is to name them as a brief, consistent trio you can recall under time pressure. One check is missingness pattern scanning, where you assess not only how much is missing, but where it is missing by segment and source, because that reveals bias risks early. A second check is duplicate detection using the intended uniqueness key and a near duplicate scan, because duplicates distort counts and can silently inflate confidence. A third check is format and unit consistency validation across sources, including timestamps, categorical normalization, and impossible value rules, because inconsistencies create artificial patterns that look real until they break your conclusions. When you make these 3 checks a default habit, you catch the majority of destructive defects before you invest in modeling, and you build results that are easier to trust and defend. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.